Okay, well, welcome to another lecture in 102. All right, so I hope you have been sort of like having a good time studying thermodynamics. Yeah, I hope. All right, and what we are going to do today is just try to sort of kicking up a notch. We are going to take everything that you have learned uh, in the past 2 weeks and sort of like put them all together in something that we're going to call it a heat engine. So now we are talking something real. Now we're going to look at an engine and we're going to apply thermodynamics, mainly the first law, of course, first law of thermodynamics, explaining how the engine works and what kind of efficiency that you can get out of this. And as promised last time that I was talking about, I am going to show you what is going to be the best engine in the universe. You will have a chance to look at that. All right. And as long as aliens using the same physics as our physics, then right, they shouldn't sort of build spacecraft based on heat engine, I guess. They're supposed to use like some, hyperdrive technology or whatever. Okay. And next time, all right, not today, we'll have a chance to take a look at these two topics over here, which is entropy. You probably have heard of this name before, or even maybe have done some calculations in chemistry or something like that. And that is the part of understanding the second law of thermodynamics. All right. And that will be the story of the next time. So this time we are going to focus on the heat engines. And one thing that you should know, this is pretty much going to be the wrap up the stories, like it's sort of like cooling it down. Well, not yet. I mean, next time it's going to be cooling down, but this time it's sort of like the peak of the thermodynamics material over here, because we're going to take everything and going to put them all into the story of understanding how heat engine works. Sounds cool? All right, so this is it. Plus, okay, it seems like the thermodynamics module is come to an end this week. So that means the exam time is about to pop up, all right? And we're going to discuss about, all right, when and what kind of things, exam number one, when is supposed to happen next time as well, okay? All right, but just so you know, it's just a matter of agreement among you guys, all right? You guys, just so you know that you guys can pick any date for the final exam. I'm not final yet, sorry. First exam, all right? We haven't had the first one yet. Yeah, it's just the first exam, all right? So that means don't worry too much. It doesn't mean like once we ended the story, we're going to take the exam right away. No, okay? It can take weeks. You can pick next week, next 2 weeks, up to you, all right? It doesn't really matter. Okay, all right, guys. So let's start today's lecture with this. This is going to be the main diagram that we're going to use time and times again, which is the main structure of the heat engine. So the idea is pretty simple, because we kind of know already, like if you have a hot stuff in thermal contact with the cold stuff, then there is a heat flow from hot to cold. Everyone knows this. So that means this is hot, this is cold. There is a direction of the flow going this way all the time. Okay. And as a human, of course, we can kind of, take benefits out of everything around us. So they just say, okay, is it possible that once we understand that this is energy that is flowing, because heat is energy transfer, is there a way that we can redirect that heat and turn it into something useful? And we're going to call it the work done. See? So the meaning of the work done by the engine seems very natural right here, because this is something that hopefully this engine can help us doing the work, lifting stuff, turn the wheels, anything, right? That's what we want out of this flow. Okay. So the question is it possible? That's one thing. And even better question, is it possible that we're going to do like 100% redirection? So that means, is it possible that we can steal the energy from the environment? Whoa. And I'll just tell you right away, like spoiler alert here. No, we cannot. All right. So if we can, we probably don't have any energy problems or whatever, already in this earth. So no, there's no way. So the question is, if that is not what kind of things that this engine can do. So by the conservation of energy, we already learned that from first law of thermodynamics. Okay, energy has to be conserved at all time. So if you cannot, there must be a leftover energy. And where does it go? The leftover energy has to continuing flowing to the lower temperature portion of the universe, or whatever whole reservoir that you're seeing on the diagram here. Okay, cool. All right, so this is going to be the main stuff that we are doing. So conclusion is this. So what we are looking at is you are going to extract some energy from the hot reservoir, okay? And of course, there will be part of it that's gonna get discarded or dumped out in the cold reservoir. And hopefully you have some left over from this that you can redirect and then use it in something useful there. And that is the work done, okay? All right, and that's it, guys. So the main diagram gives you this: the amount of heat flow in, the amount of heat discarded, we call it the Q cold, and the work done by the engine. As you can see, because we already agreed about the directions, heat flowing in is positive, heat flowing out is negative, on and on. But we don't want to deal with that directions anymore because the direction is so obvious right here. So what I'm thinking of doing is just like, hey, why don't you just take the value of that? Okay, so we just do, okay, just the heat flowing in. And if you want the leftover, so that means there must be a heat flowing out with that amount. And you just take these two amounts and then you just do the difference. The difference has to go into the work done by the system, and then you are done. Okay, and this is the equation that it's written right here. Okay, cool, guys. So this is what we want. So what we have over here is just a big diagram, a main diagram that's showing what is going on around the heat engine. You have to sort of like pull in the energy, try to turn it into something useful with the work done. And then, of course, you still have something that you cannot turn into a useful work. You just have to dump it out. Okay. Second, because you want to do this over and over again, so you hope that you still continuously pulling in the heat. Yeah, just keep coming. And then you hopefully that, okay, just keep generating the work done, just keep going. So you want the engine to run in cycle. You guys with me? Yeah. That's the reason the cyclic process comes into play. So that's why there was a diagram that you discussed or that you analyzed before that looks like a complete cycle. And that's what this one is for. So you hope that each cycle, it can do the draw in the energy, turn something into work done, dump out the heat, and just start all over again. And then you do the cycle repetitively. Okay. So with that, we learn one thing about this is the internal energy of any cycle will give you a zero change. Yes. Okay.
Okay.
The reason is because energy is path independent. So when it's path independent, you come back to the original position, no energy change. All right. So from the first law of thermodynamics, I'm going to write this down one more time. When the delta U is gone, you got to get the change. That looks really weird here. I'll explain in a little bit, but at least you know that the heat is going to be the same as the work done. But because right now we have like a, multiple heats flowing around. So there is the word delta over here that I just throw in this slide over here. So this delta means this difference right here. That's what this is. That's the delta. Okay, so the delta mean, all right, there's a portion of the heat that flow in, and then you have to do the difference with respect to the heat that is flowing out. So the difference between the heat come in and go out must be equal to the work done. That's it. Okay, it's kind of long, even though this slide looks like simple enough, but I hope this give you like an infrastructure of everything we're going to use. Okay, but thing is going to get more complex over time when we attach this whole thing with the real process in like PV diagram, for example. Okay. All right, cool. So how can we express the sort of like the ability for this machine to turn incoming heat into some useful work? So we just define, I think this is the word that you guys sort of agree, efficiency. So what you want to know is how efficient this engine is running. All right. The better efficiency means you can take heat that flowing in and turn it into some useful work really well. All right. And the best thing that is possible, if you have like a perfect efficiency, then you have 100% efficient engine, even though we said that's not the case. All right. So what should be the definition of the efficiency, guys? All right, don't need this. Concepts, it's very simple. What you get divided by what you have to supply or you have to provide to the system. Does that make sense? So think of it like studying physics right now. So the efficiency of your learning is this, like how much material that you can put into your head, right? That's what how much you get divided by how much I provide the material to you. Does that make sense? Or you can think in terms of time. You studying like 1 hour, how many minutes that you're gonna like, you know, have concentration and then try to understand the material, stuff like that. All right. So the concept is simple. It's just what you get over what you have to supply or provide to the system. Okay. Looks good. And what you get is, of course, you want to get this. You want to get the work done here from this system. Okay. And what you have to provide, of course, it's a Q hot right there. So it's an incoming heat. So by definition, the efficiency is defined as the work done over Q hot. And because efficiency is just a number, it's never going to go negative. So that's why there are absolute sign here everywhere, because all you care about is just a number. And that number is going to go between, of course, 0 to 1, right? 0 means you get nothing out of it. 1 means you get everything out of it. All right. You can multiply this by a percent. So you can go from 0% to 100%. That depends on the units that you want to work. Okay. But the efficiency is just unitless quantity, no unit. It's just a number. Okay. Now you can use the expression that we just saw before. Okay. The work done is just the difference between the Q hot and Q cold. Yeah. All right. You can just, you know, substitute that in, and then you can rearrange this and that if you like. So this is whatever you want to pick one of these 3 expressions for a definition of the efficiency. Okay. One thing that I like about the last expression is this. If you notice over here, the efficiency is 1 minus Q cold over Q hot. So this is sort of, we can understand the last portion of this expression kind of like intuitively. If you want the efficiency to go super, super high, what you need to do is just, you need to minimize this. Make sense? All right. The less of the heat that you discard out in the whole reservoir, the higher the efficiency that you are getting. Okay. The best if this go to 0, which I say it again, that's not possible. But anyway, that's what it is. So what it is this last part of the expression just saying you, okay, all right, if you don't have anything to throw out at all at the core reservoir side of the engine, the better the engine is running, because that means the engine can turn the incoming heat into more work done. Okay, cool, guys. All right, so far so good. All right, this is a fun fact, and just so you know, the diesel engine, all right, even though you know, guys, like diesel engines seem to run more efficient than just like a gasoline engine, but what you have over here is the efficiency is not going to be more than 40%. Isn't that amazing?
Okay.
So that means you pretty much throw the energy out, like more than half. And where does this go? The engine is running hot. So when you touch the engine is super hot. That is the heat that is useless. Too bad. Okay, so that's the discarded heat into the environments and everything. Okay, so you can only turn about 35 to 40% of the energy from the, of course, you have to do the combustion, right? You put in the fuel, the gas, and it combusts, bam. And then you turn the chemical energy into some thermal energy, and then you extract that. Part of it, turn the wheel, the rest go into warm up the engine. And that's the useless heat, pretty much. Okay, cool, guys. Okay. Any questions so far? Okay, so if not, dive into this simple question first, just to get you going today. Get you going. I don't know. Still having fun, I hope. The gas engine burns 0.2 gram of fuel and delivers 2,000 joules of work per cycle. All right, so that's cool. So you burn this much gas, and then it turns out what you get over here is 2,000 joule per cycle. So this is your W right there. All right, now, given that the heat of combustion is 5 times 10 to the fourth joule per gram, even though you don't know the word heat of combustion. But when you look at the units of this one, you should be able to guess what this means. It's just joule per gram. So the idea is just like the latent heat. Okay, so you just know the amount of energy per gram of whatever the material that you are dealing with. But over here, you just say, okay, that means each gram of the gas or the fuel, if you combust it, you're going to get 5 times 10 to the fourth joule. That's it. Okay, so we just sort of call this one nicely heat of combustion. Okay, so the idea is just like Q equal to ML. So I can just draw it like this. Yeah, but now the Q is just heat from the combustion, right? Now find the heat discarded in each cycle and what is the thermal efficiency of this engine. You want to give it a shot? Whew. Okay, maybe not. I'll do it. Okay, so let's calculate first. Because you burn 0.2 gram, okay, so just multiply this by the heat of combustion, so you know how much energy you get from that combustion. So you just times 5 times 10 to the fourth joule per gram. Yeah, cool. Gram units cancel. So at the end, you get 10 to the fourth joule. So now burning 0.2 gram of fuel give you 10,000 joules. Cool. And now let's draw the diagram again. So now you can, So now you can see that that is your incoming heat. That is actually Q hot right there. You guys with me? Yeah, because that's what you provide to the engine. So that is your Q hot right there, 10,000 joules. And the problems already give you information that this engine can turn this incoming heat into 2,000 joule of useful work, turn the wheels or whatever. So now you know right away what should be the discarded heat, guys. Of course, it's going to be 8,000. Yeah, everything has to add up. Okay, and that's it. From here, you know right away that your discarded heat. Okay, let me just just to make sure that you won't confuse with the sign here. Just put the absolute here, just so because we know the directions of the heat flow already. So what we have over here is now already answer your first part. The heat discarded is going to be 8,000. And what about the efficiency, guys? All right, now you know everything. So you do whatever you want. The work that you get over the Q that you have to provide to the system. So it's going to be 2,000 joule over 10,000 joule. And that's it. So your efficiency is 0.2, or you can multiply by 100 and say it's 20% efficient engine, and you are done. All right then. Okay, so this is like just like a warm-up question. Just make sure that you understand the whole structure of heat engine. It's not very complicated at all. In, something out, and the rest go to something useful work. 3 components here. All right, any questions so far? All right, if not, keep going. Okay, so before we dive into some more, quantitative calculations and get you to work on the PV diagram and everything in detail, just like last week, what if, what if, some of you probably wondering, Ajahn, can this be run backward? Can we go against the nature a little bit? Of course you can, right? If you reverse the direction of all the arrows that you saw in the heat engine diagram, what you are doing is you're trying to extract heat from the coal reservoir, and then you try to dump it into something hotter, which is sort of against the nature a little bit. So this is not going to happen by its own. You guys with me? You cannot transfer heat from cold to hot. That's not the right direction. Okay. So the only way that you can do it, you have to supply that engine with some extra work. So you have to reverse all of the arrows. All the directions of the flow has to be reversed. Okay. So that means you have to supply some work. So you will be able to pump the heat. You guys with me? All right. The concept of the pump is just like what you have with the water pump in fluid dynamics or whatever. So every time that you want to take the water from the lower level to a higher level, what do? You have to pump the water. So you need a water pump because the water flow from high to low, and anything flow from high to low naturally. So if you want to bring the water from low to high, you have to have a pump. Okay, if it's the water, that's a water pump. But now we need the heat to flow. So we have there you go, guys, heat pump.
Okay.
Okay, and the way that you do it is you have to supply this pump with some energy. Just plug in. If it's an electronic heat pump, something like that. All right. But for us, what kind of heat pump that you sort of familiar with and pretty much uses it pretty much all the time? Yeah, is a refrigerator and air conditioner. You guys with me? Okay.
Okay.
All right. So the reason for this is you think about it, you are in this room. Let's say this room is air conditioned. So the air conditioner is trying to bring the heat from the inside the room, which has a lower temperature. You see that? Right now, inside the room has a lower temperature, outside is hotter. So the air conditioner tries to take the energy from the colder place to the hotter place. So air conditioner is the heat pump. Same thing with the refrigerator. Okay. You inside the fridge is cold. Behind the fridge is hot. Okay. You try to keep pumping the heat from the inside the refrigerator to the outside. Okay. So refrigerator is another heat pump. Okay. And what is the supply of the energy? Just plug it in. All right. I mean, you just need, motor, condenser, and everything to run, So you have to supply the energy to these heat pumps. All right, cool, guys. So that's it. So once you get that, everything else pretty much works the same way because everything has to go along with the first law of thermodynamics, or even just saying that it's a conservation of energy. So what you have over here is the Q cold, the Q hot, and the work done just pretty much has to add up once again. So what you see is the W, okay, along with the Q cold must eventually combine and just dump it out into a hot reservoir. That's it. It's pretty much the same equation actually. But right now we're just focusing on, the other side of the equation or whatever, but they are just the same equation. Okay, guys, looks not too bad. Okay, and if you would like to define the efficiency of a heat pump, you can do it too. Same concept. What do you get over what you have to provide? What are you getting? Guys, what are you getting? Well, Ajahn, I'm getting this. I want to get a lot of this. The better the air conditioner means you have a more ability to take away the heat from inside the room and dump it out. Does that make sense? So what you're getting, you try to get the big amounts of Q cold. That's what you try to get. So you see, okay, what you get, what you have to provide, you provided work. See, so that is the concept that we use in efficiency before. However, this number can go beyond one. And that doesn't make sense if we still use the definition of the efficiency, because efficiency shouldn't go beyond one. That's kind of weird. You put in one, you get back two. That's against the nature. So we don't want to use this terminology anymore. So we're going to call it coefficient of performance. Okay, guys? Okay, and that's pretty much give you the definition of the coefficient of performance. However, however, this is the heat pump, and you are concentrating on what you're trying to get in the cooling modes, because we look at the air conditioner, we're looking at the refrigerator. So you want to look at how well this thing can cool things down. Okay. So that's why we're going to call this the coefficient of performance in the cooling mode. However, it's the same however. But the reason we have to put this word, because there might be another scenario that, hey, I'm already in a cold country. I don't want any air conditioner. What I wanting is I want to pump the heat from the outside, which is colder, into the house, which is hotter. So you see what I'm saying? So the utility of this one is more like you are concentrating on the hot portion of this. If that is the case, you have to turn this, what you get, into Q hot, because you want to get a lot of hotness. You want a lot of heat. Okay. If that is the case, That will be the COP, the coefficient of performance in the heating mode. Okay, but the reason that I'm strict ourselves with just the cooling mode is because mostly we are, we are in a tropical country, and then it's pretty much very hot, and we want air conditioner. Yeah.
Okay.
Okay. All right, but at least you understand the concept, right? It doesn't matter is it efficiency or coefficients of performance. The concepts behind this is simple. What you get or what you want to get divided by what you have to provide or supply to the engine. Okay. All right. Very nice. All right. So that's done. At least I get this one out. And I hope you now understand air conditioner and refrigerators based, sort of with the underlying thermodynamics in your head. Next. All right. Here we go. The fun is about to begin here. So we already saw that the main diagram was just simple. Heat flow in, there's some work done, the rest go to the cold reservoir. But then what is really happening is there must be some process that is actually happens to the substance that we use in that engine. And of course, you can guess what are we going to use is going to be ideal gas. Yeah, of course. We're not going to use anything else. It's too difficult. Okay. However, there is other thing that is pretty much interesting. And by analyzing this process, or this scenario over here, will eventually lead you to the best engine in the universe. Are you ready for it? No. Okay. All right. So consider this. I think you guys familiar with this already. All right. We have done this already like a couple of times. So take a look at this. You have, once again, a gas in an insulating wall container. So it's insulated container. This will not allow any heat to flow in or out. No heat flow for sure. Plus, the gas is being confined in the bottom half of the container by some membranes, whatever. So let's say the gas initially has some temperature and has the volume just half of the whole volume of the container. Right, cool. And because this container does not allow to expand or shrink, so that means already saw it, no work done is going to happen here as well. Now, once the membrane just pretty much expire or whatever breaks, so the gas just expand and fill up the whole space inside this container. So what you get over here at the end is the temperature will not change because you do not allow heat or work to do. So the delta U will also be 0. All right, you saw this already. However, the volume is twice as big. If you call this the V naught, so this is going to be 2 V naught. But from the equation of state, you guys know that if this is the initial pressure, at the end, you're going to get half of the pressure, right? Because PV equal to nRT all the time. And this, you already saw from last time, this is an isothermal process because temperature does not change. Okay? So when the temperature does not change, this is going to be on the same isotherm. All right, that's it. All right, that's what's a review. But then the point of this one is, this process is irreversible, guys. Whoa. Wow. Everyone knows that because it's pretty much impossible, even though you might say, yeah, there are some, there is some probability that this might happen, that all of the gas molecules just decided to, hey, just gather around at the bottom half of this volume of this container. But the probability of that to have that incident is going to be like, you have to wait maybe longer than the age of the universe for this to happen, so even just a fraction of time. So you can safely say that this is an irreversible process, guys. Okay?
Okay.
Cool. All right. But then, Mojan, I don't like that irreversibility. So if you want something that is reversible, look, so let's compare this to the scenario on the right. So you have the same gas, let's say same volume, same initial pressure, same initial temperature. Yeah. And then because right now the system is different, your gas over here is now in thermal contact with the energy reservoir. And you saw this example already. So if the energy reservoir is already at the same temperature, T sub I, this is going to be another isothermal process as well. Okay. However, on the right, now you have a piston that is movable. So you allow the gas to expand or contract a little bit, depends on interactions with the external force. Cool. And then you imagine, all right, this is not a real experiment on anything. Huh? Just imagine this. So you just imagine that you have a sand, like a bunch of sands, and then you just pour that grain of sands on top of this piston. All right, so you put some weight on the top, and then of course you can compress the gas down just a bit, and then you just keep pouring in a little bit, right? One grain at a time, or whatever you can do as slowly as you want. So you get some compression, but then you can change your mind. Whoa.
Okay.
You're just like, okay, John, I wanted to expand back. So you just pick up each grain one by one again, and then eventually you allow gas to expand back to its original position. So from the look of this imaginary scenario, it's just trying to show you that if you do things slowly and you try to make things sort of like nice and cool and slow and everything, it's still a reversible process. And now you can see from here, you have to do things very, very slowly. This is the word that you encounter once, if you remember, quasi-static. So it's, you sort of see the relationship between what this word is trying to tell you, right? We mentioned briefly about this. It's like, hey, in thermodynamics, when you do something, you have to do slowly, let the system adjust itself until everything reaches the equilibrium. So you can measure the pressure, you can measure the temperature, everything nicely, and then you move on to the next step. This is the step that I'm talking about.
Okay.
Okay. Is the step that just have to put, the grain of sand is like one grain at a time, do things slowly. So like, it's kind of like, okay, it's a shame a little bit, like in reality, nobody will do this, but understanding this kind of imaginary process allow you to understand thermodynamics, and it seems to work fine. Okay. All right. So this is the distinguish between the reversible process and irreversible process. Isn't that cool? You're probably like, not cool, John. What's the point? What's the point? The first point is this. Every process in the world, I can't even, I might be able to even explain it to every process in the universe. But maybe that may be a little bit too strong of the sentence. So that's why, okay, just keep it to just in the world is irreversible, guys. All right, we'll have a chance to discuss more about this next time when we discuss second law of thermodynamics. But this is something that you can relate to. You guys getting older, and that's not reversible. Yeah, things get scattered, get messy, get chaotic, get dissipated, get distributed, or whatever. So when things started out, everything is nice and clean. You can think of it like your table, your working table, for example. When you just bought a new table, it's just clean. There's nothing on it. And then from time to time, not time to time, then as time goes on, you put this here, there's a books there, computer, the notebook, I mean, the stationery and everything, right? Things get crazy. And that is pretty much, it's irreversible by itself. Right? The table is not gonna sort of like clean itself or put things in order by itself. You have to put some work into it. You have to line up the computer and clean things up, put this in the box or whatever, sort of like put them in order. But in general, the process that things are going in nature is irreversible. Just keep going, right? You're never gonna get younger. Okay, so what's the point, Dan? What is the point? Okay, the point is this. Now let's come back to our business in thermodynamics here. So look at the first scenario up top. When you have a metal box, and if this box is hot, 7 degrees Celsius, inside there's an ice at 0 degrees Celsius, it's gonna melt. And eventually the metal box and the ice will come down to some moderate temperature at the, like, let's say somewhere in between 0 and 70, let's say it's at 60 degrees Celsius. And you guys know there must be heat involved in this process. Heat will flow from the ice into the metal box, right? And then you did this calculation before. You say, okay, Q equal to ML plus MC delta T, blah, blah, blah. And then you say for the metal box, Q equal to M box C delta T, on and on for the box. Something like that for the ice. Right, I don't need to do too much of this one. But anyway, the idea is there is some involvement in the process that related to heat. There is some heat flow during this process. All right. So I think I can erase this. It just doesn't need it. Okay. So the heat that's involved in this process, you guys know, is irreversible. It's gone.
No. Okay.
Yeah. So it's no or okay.
Okay.
Right. Because the metal box will not heat itself up, or the liquid water will not get frozen again. So the heat involved in this process is the heat that has been used and gone forever. When I say gone forever, it means there's no chance for this heat to be able to make use of this and do something useful anymore. Does that make sense to you guys?
Okay.
Right. So that's why I put the sort of like the word over here is you cannot bring back this heat. So this heat has no chance of doing something useful to you anymore. All right, now let's contrast this scenario with the bottom one. But let's say now you have another scenario that the box seems to happen to be at 0 degrees Celsius. Okay, and the ice is also at the same temperature. All right, so from time to time, right, you might not be able to control this one, but the key is, all right, there might be the heat flow from the metal box to the ice, or the ice just, decided to change the shape a little bit and just melt it down or whatever. But the thing is, everything happens at this same temperature at 0 degrees Celsius. So if there is something to happen, like a melting process, you cannot control the microscopic level of this whole thing. So, there'll be some time that, all the molecules decided to arrange a little bit, right? So it seems like what you're looking over here is the heat involved in this process is not going anywhere just yet. It's not going anywhere. All right. Oh, there's a question come in. So when we apply work, does it become reversible? All right, that's a good question. We will have to take a look at how you do that work. But the thing is, when you do apply work, the work transfer the energy to the system. Does that make sense? Okay, because the work is energy transfer. So that means when you apply work, that means you already increase the energy of the system. So your attention goes to the system. If you are dealing with the system that is still reversible, then your things that you already put in there is still reversible. I don't know. Does that make sense to you? Yeah. So it depends on the energy that you supply to the system go into the reversible or irreversible process. Yeah. All right. So I would try to say it has nothing to do with the way that you try to supply the work. Because when you say you do the work, you give the system some work, that is the energy transfer. You already complete the transaction. Okay. And the rest just depends on the system. Okay. All right. That's a good question, actually, because I can understand that it seems like, there is some connections there, and it's like you might want to ask beyond the system at some point. All right. But I try to bring you back here. It's just like, okay, just focus on the system. Okay. So what we have over here is the heat that's involved in the constant temperature. You can see that the temperature of the ice and the temperature of the box are at the same temperature. Seems like the heat involved here, it still flow back and forth. So it's like, it's still with us. Okay, it's not going anywhere. So these are the two contrast scenario. So it seems like the reversibility seem to link to the heat that is available to you or not. Does that make sense to you? Okay, one more time. It seems like up here is an irreversible process. So when things are irreversible, if you have any heat associated with this process, that heat seems to be a lost one, the one that you won't be able to take back and do something useful with it. But if you have a reversible process, the heat that you are dealing with during this process, it's still not going anywhere. It's still running around in your system. And then hopefully you will be able to do something useful with it. Yeah. All right. So that's what we are trying to get to. So the conclusion is this. Think about it. When you want to generate a very good, efficient engine, what do you want? Of course, you want the W. Okay, let me once again draw the diagram for you. So you sort of try to have you get sick of this. There's a Q hot, there's a Q cold dumping out, and there's a work done, right? So when you think about it, whenever you want a high efficiency engine, you want to maximize the work done. And because now we know the work done is just a difference between the Q hot and the Q cold. And this is the portion that you can sort of like imagine like, okay, the more of the discarded heat, the less efficient. So that means you want heat that involves within the cycle of the engine running to be as useful as much as possible. Does that make sense? You don't want the heat that's sort of like useless. I don't want useless heat. I want heat to be within my system, and I hope that I can turn that into something useful. And that's conclusion. The conclusion is you cannot avoid running the heat engine between two temperature. There must be T hot and there must be T cold, because that's a heat engine. It has to run between hot and cold temperature somehow. So you cannot avoid heat. You cannot avoid heat. It has to have some heat transfer, but you want to maximize the useful heat. You want to maximize the heat that can still turn into something useful. And you want to minimize the heat that is useless. So here's the conclusion. If there is a heat transfer, that you will definitely going to have heat transfer. You want to do it at constant temperature. See, because we already agree, this is a bottom case. If there is a heat transfer and you do it at the constant temperature, the heat is still with us. It's still reversible, not going anywhere. So you want to do that using isothermal process. Does that make sense? I think the slide is kind of lacking to you guys. Is that right? I think so. Yeah. I just had this issue for a while, and I think I figured out it's because of the way that my new notebook is communicating with the internet, I guess. I think it's the internet lagging. I don't know. All right. But anyway, it's still not too annoying. Still keep going. All right. Here. On the other hand, all right, that's one part. If you need the heat transfer, please do it at constant temperature, isothermal process. However, you still have to change the temperature, because you have, temperature cannot be fixed at one point. Heat engine had to run between two temperature. So if the temperature needs to be changed, we don't want this. We don't want this. Okay, because you can see there is some change in temperature going on. So what we want to prevent the heat loss during temperature change. And that is the adiabatic process, right? We saw this before. Perfect. So we are going to build the engine that based on these two processes, isothermal processes, isothermal process, adiabatic process. If you can combine these two processes and build a cycle that representing an engine, that engine will be named Kernel engine.
Okay.
Okay. And Kernel is the French engineer who came up with this whole conclusion over here that this is going to be the best engine in the universe. Nothing can beat this one. So this is the upper limit of the efficiency of an engine in this universe, running between two reservoirs, hot and cold. All right, come again. So what cycle is that? Okay, here it is. This.
Okay.
Yes, Kernel cycle. Okay, so let me sort of give you a whole idea over here, and then we'll get down to the conclusion. All right, which is kind of easy. That's nice. So you start from here. Let's say, guys, focus on point A. You need to draw in the heat, right? It's a Q hot, Q hot, Q hot. Okay, so you want heat to flow in. So during the heat flowing, you want to do it at the constant temperature. So that's why I follow my yellow curve here, guys. See, that is isothermal process. Remember, every time that we seeing a PV diagram, just imagine that you have an isothermal line, you know, in your imagination or whatever. There you go. All right. So you want to draw in, you want to pull in the heat. Let's do it isothermally, guys. So you're riding along this isotherm up here. So going from A to B, that's isothermal process. You draw in the heat. So that is an incoming heat. That is a Q hot that we are talking about. And the arrow is pointing down right there. Cool. First step done.
Okay.
Now, because you cannot run the engine at this temperature, you have to lower your temperature down to a lower temperature. So there is a temperature change going on. So when the temperature change going on, you want to do it in an adiabatic process. And we remember that adiabatic process is the curve that is steeper than the isotherm. So that's what the green one is. Follow, oh, sorry. That's the green one is, right there, from B to C. There you go. See, so I'm jumping down from higher isotherm, higher temperature, to a lower isotherm, lower temperature. Now I'm arrived at point C. Okay. Then, of course, you want to shoot everything back to A. You want to go back to point A because you want to complete the cycle. And during that process, you have to dump out the heat because, I mean, that's, you cannot just shoot back to A given that you want to do isothermal process. So that means you want to go back a bit so gas get compressed. Okay, down here from C to D. Okay, get compressed. But during that compression, you have the heat flowing out. That is your Q cold. You have a heat exchange. You want to do it in the under isothermal process. Is that cool? Nice. All right. Now, once you are here, it's our time to get back to A now. All right. Now you're already at point D. Now you want to shoot back to a higher temperature. So there is a temperature change. You want to do it isothermally. So follow my red line here. There you go. Jump it back up again right there. Right there. Okay. And that is the another adiabatic process. No heat exchange. And then you go back to point A, complete the cycle. That's it. This is the Kernel engine, guys.
Okay.
All right, nice. I hope it's nice. Okay. And this will give you the best engine in the universe. Okay. And after the break, I will show you how to calculate the efficiency out of this. And we will have a chance to answer why can't you use your temperature body to charge your smartphone? Yeah. That's a reason for it. All right. So that's after the break, guys. So let's take 10. Yeah. Recording this one first. All right. So how to calculate the Kernel engine efficiency? Of course, concept stays the same. It's still the efficiency is just a ratio between the work and the heat that you provide to the system. Okay. And of course, you already learned all these stuff since last week. So what you saw over here is if it's isothermal process, you have delta U equal to 0, and then you can calculate the area under the curve, and it's an nRT log V final over V initial, on and on, right? So for the isothermal process, no problem. For the adiabatic process, you already saw that you have to use like PV equal PV to the gamma equal to a constant. So you can turn that P and V into T and V or whatever you like. So that means I can also write the relationship along the adiabatic process using that PV to the gamma equal to constant. All right. So from these four equations, you can just, mix and match, manipulate this and that, and then try to come up with a nice relationship among these parameters. And it turns out, oh, welcome to the conclusion.
Okay.
From all the equations, we get this. The conclusion for the Carnot engine is simple. It turns out the ratio between the heat that flow out and the heat flow in is the same as the temperature. With me? So the ratio between Q cold and Q hot equal to the ratio between the T cold and T hot, and you are done.
Okay.
You can replace this ratio back into the expression that we derived for the efficiency. The last one, the last portion of that expression, we say efficiency is 1 minus Q cold over Q hot. Now you can replace that with the ratio of the temperature, and that's it, guys. This is the best engine in the universe.
Okay.
Wow. And this will sort of, crack what the thing that I said. You want to get efficiency 1 engine, you have to make sure that you have 0 of this, right? Remember, if you want efficiency equal to 1. But because the best engine that you can have is this Carnot engine right here. And this ratio is the ratio of the temperature. So to get the efficiency of 1 out of this Carnot engine, you need the 0 Kelvin T cold. That's not okay. 0 Kelvin. Okay.
Okay.
And that is not possible, guys. Because we just said 0 Kelvin is unattainable temperature. That was the third law of thermodynamics. So that say this Carnot engine just guarantees that there will be no machine in this universe can turn heat into work with 100% efficiency. Not possible. Cool. You mean observable universe?
Okay.
Of course. Yeah. For an unobservable, then that will be an unobservable subject, maybe. Okay. We don't know what's out there. Correct. Like a multiverse, maybe. That would be another Spider-Man. Doctor Strange might know better on that one. And the arc reactor in the Iron Man is probably not gonna follow thermodynamics anyway. Okay, yeah, very good. Yeah. So as long as we sort of like stick with the universe that we are observable around us, the ratio between the temperature T cold and T hot give you the efficiency of the Carnot engine. So we put the subscript C just to signify that this is the efficiency of a Carnot engine, and it's going to be the upper limit of the efficiency among any engines that operating between these two temperatures, the T cold and T hot. Sounds good? All right. So see, the nice thing about this one is the conclusion is very simple.
Okay.
Just take the ratio. And all you need to do is just figure out the temperature of those reservoirs. And that's it. All right. You will be able to calculate the best efficient engine in the universe. Okay. So just to give you a clue, what does it mean by a Carnot engine and other engines? So this one, all right, we're not going to dive into the detail of how this cycle works because they're trying to use this cycle. There's a name for it. It's an Otto cycle. This cycle is trying to explain what is going on in your car engine. Okay, the one that pump in the fuel, combust the heat, move up the piston, and then once you inject and then do the combustion right there, you compress it back down. You do the move of the and on and on. That's the whole thing. Let's say we just don't worry too much about it. But let's say if we can model those processes, the cycle of the movement in the cylinder in your car engine, to be this PV diagram right here. So as you can see, the shape of this one is not going to look like Carnot engine because the Carnot engine is supposed to have 2 isothermals and 2 adiabatic process. But over here, you might have like here 2 adiabatics and you have two constant volume processes, whatever. So what you can expect here is the efficiency of this engine will be less than the efficiency that you will get if you were to replace the engine by the Kernel engine. Okay?
Okay.
All right, that's good. So we will have a chance to calculate the efficiency of this kind of cycle. I mean, not exactly like this, but any other cycles. And then you can do the comparison with a Kernel engine. All right, we'll see in the example right here. All right, so before we dive into that, let's do like a quick intuitive question first. You have three engines operate between reservoirs separated in temperature by 300K. All right, so it's a fixed amount of the temperature difference between hot and cold reservoir. The reservoir temperatures are the following. So you have 1,700, 800, and 500, 600, and 300. You guys, what do you think? Which one will give you the highest efficiency? In theory, of course. Right. So they want you to rank the energy in the order of theoretically possible efficiency. You want, theoretical outputs. So you think of the Kernel engine. All right. So let's give it a shot. So the efficiency, all right, I'm going to put the Kernel engine right there because that will be the best that you can get. 1 minus, you can turn this ratio between Q cold and Q hot into T cold over T hot. All right. So what I can do over here is I can do efficiency of the engine A is going to be 1 minus 700 over 1,000. And that will be 0.3 if my math is correct. All right. And you can ignore in engine B because it's somewhere in between. So it's going to be competing between either A or C. So for the case of engine C, you get 1 minus 300 over 600. Yes. And that is 0.5. Very good. So at least now you can see that, okay, engine C is supposed to have a higher efficiency. And that's going to be the number one efficient engine that we're going to pick. All right. And the A will be the least efficient engine among the three. But just for you to get an idea, right? This one, I mean, you can do the calculation easily, 0.3, point whatever, 0.5, that's fine. But let me give you an extreme condition over here. What if my T hot is at 1 million Kelvin? Whoa. Wow. All right. So that means the T cold is going to be the difference of the 300. So it's going to be 1 million minus 300K. Okay.
Okay.
And now I give you another scenario. So let me call this engine D. And let me call engine E. The T hot is at 300.1 Kelvin. And T cold is at 0.1 Kelvin, right? Because I tend to write 300K and 0, but now we already know that the 0K is not possible. So let 0.1 to it. Just add 0.1 to it. Okay. So which one will give you a high efficiency among these two, D or E, guys? What do you think? Of course, you can guess what, Ajahn, it's going to be E. Now you can see why now? Because your low temperature side of this is almost at 0K. So you imagine that you're living in the world that your environment temperature is at 0.1 Kelvin. And suddenly there is an engine that operates between your environment and 300. You see? So the 300 difference will look huge to you, to your environment. So with that huge difference, you should be able to do a lot. So that's why the efficiency is so high. But now you are, let's say you're living in whatever the star that has like a 1 million Kelvin temperature environment. So you're living there. And suddenly you look at, all right, there is an engine that operates between 1 million and 1 million that's, short by 300. You won't feel a thing, right? You don't see any temperature difference. It's like, okay, I don't care. So that means you shouldn't be able to make any use out of this. So the efficiency of D will be super low in comparison to efficiency of the engine E. Does that make sense? Okay, so that's my point. The point is the lower of the lower temperature, the lower of the temperature of the cold reservoir, the better the efficiency. That give you the same conclusion that we saw over here is, yeah, the best efficiency engine in the universe will happen if you can manage to have your T-core to be at 0 degree Kelvin. If you cannot manage, at least get as close as possible to 0. Okay, so any difference from that 0 will be huge to you. Okay, does that make sense? All right, and this reason right here, this is a reason why now you can answer my question, my sort of observation that why can't we use our body temperature to charge your smartphone? Because our body temperature could be like, let's say, 37, so 310 maybe, somewhere around there. Okay, and then the room temperature, let's say approximately about 300K, yeah, approximately. So that means the temperature difference is only 10 Kelvin. So if you were to have an Kernel engine and turn it into, like, have an interface, put it in a USB whatever cable stuff. So your efficiency that you're going to get is going to be the Kernel engine efficiency. All right, this is engine, right? Not the Kernel engine. Yeah. Okay, what you're going to get is going to be 1 minus 300 over 310. Okay, and if you work this one out, the efficiency will be somewhere like, a fraction of a percent. So, I mean, sort of, let's say just one single digit percentage that you're going to get, like, let's say 4% maybe. All right, but that is going to be the best case scenario already. Yeah, so it's going to be like, okay, but John, that even if you have Kernel engine, you only get like 4% efficiency. And in real life, you're not going to have the Kernel engine. You're going to have engine that's pretty much have frictions, have this, has that. And if you have to convert into electricity and all this stuff, you have resistance, you have, loss at the boundary, at the interface and everything. So you get like a fraction of a percent efficiency. So who will be able to do anything useful out of it? You put in 100, you get out like 0.1. So that would be the ugliest energy converter possible right there. Okay, so this is the reason why, okay, you won't be able to use temperature difference that only very small to generate something useful. That is because now the best engine that can do that, which is a Kernel engine, can only do this 1 minus T core over T hot, and that's it. You cannot go above this number right here. Sounds cool?
Okay.
All right, but at least now you understand that if this kind of device can happen, whenever you get a cold or get sick, you get some flu, your body temperature is higher, then you know that your efficiency of that USB port will be better. If you want to use your body temperature to charge your smartphone, yeah. So when you have a higher, you have fever and everything, then it's like a fast charge there. Okay, that's just me being silly here. Okay, all right, guys. Next, try this one. All right, this one is sort of another warm-up question. You have a Kernel engine takes 2,000 joules of heat from a reservoir at 500K and discards some heat at 350K. Find the work done by the engine, find the heat discarded. All right, so now it's going to be pretty straightforward to you guys now. You have a main diagram over here. It takes 2,000 joules of heat coming in. That is your Q hot. Let me just care about just the number. All right, so that's your Q hot right there. And it turns out the temperature. The temperature of this one is 500K. You dump out your heat at 350K, but you don't know the amount of heat just yet. Okay, so find the work done by the engine because this one is a Kernel engine. So the good thing about this one is you know exactly that the ratio between the heat is going to be exactly the same as the ratio between the temperature, and you are pretty much done. So what you have over here is your Q core is going to be T core 350, T hot 500, Q hot 2,000 joule. And that is it, guys. It's going to be 1,400 joules. That's your Q core that you can put it right here. And from the conservation of energy, now you should be able to answer right away that, of course, the difference between the hot and the cold is going to give you 600 joule as a useful work. And that is your W right there. Cool? Already. And you can even calculate the efficiency if you like. This is the efficiency. I just put the subscript there just to, once again, this is a Kernel engine. And it's going to be 1 minus T cold over T hot. Or you can use the ratio between the heat, that is fine. 1 minus 350 over 500. And that is what? 30%, is that right? 150, yeah, I think so. 30 degree, 30%, sorry. There you go. All right, something like that. Very good. Okay, and you can get 30% out of, here you go. It's a 600 divided by 2000. Same idea. Okay, it's going to be 0.3 efficiency. Very good.
Okay.
All right, keep going. All right, this is still sort of like, okay, John, this is kind of all right, doable. Now, we're going to get more realistic right here. So this is getting closer to the real stuff that we're going to, put in the not final, just keep talking final exam. In the exam, it's going to have something like this. You're going to get like a PV diagram that's showing how the engine works in detail. And then now you start to answer the question about, heat, gas, efficiency, everything. And now you see that why the first law of thermodynamics that you learned in the past weeks will be very useful right here. Okay. All right. Let's dive into it, guys. Let's go for it. Oh, I have more space here too. All right. So I'm going to work through this and then this is going to be the big example of today's lecture. All right. And we can throw the rest to the next time. So you have, some time to think about the material that we study over here, maybe review a little bit if possible. Maybe not. But anyway, all right, let's say if this makes sense to you. You have a heat engine operates using a cycle shown. All right, very good. So from the look, it's still not too bad. It's only 3 segments process. Working substance is given to be 2 moles of helium gas, which reaches the maximum temperature of 327. All right, so one thing I can do is I can turn this into Kelvin right away. So you just add 273 to it. So you get 600 Kelvin. All right, so far so good. Now assume that the helium can be treated as ideal gas. That's the only way we know how to treat the gas. Anyway, the process BC is isothermal. That's nice. So every time that you see a PV diagram, at least imagine that you have an imaginary imaginary isothermal curve right there. So the BC line should be right on this isothermal curve. Okay, so the pressure, the pressure at A and C, which are at the same temperature, are given to be 10 to the 5th Pascal. Very nice. And the pressure at point B is also given. Very good. And it says it's 3 times that of pressure at A. All right, now, guys, are you ready? How much heat enters and leaves the gas each cycle? Woo!
Okay.
All right, this is serious. How much heat enters and leaves the gas each cycle? Now you don't have, even though you can draw the main diagram over here, there will be Q quad coming in, Q cold going out. There's a work done over there, but now you have to calculate those heats by yourself based on the PV diagram that you have on hand. Okay, so we're going to attack this one segment by segment, one segment at a time. So let's start from A to B, shall we, guys? Okay, so the goal that we want to get to is what is the heat during each segment. And once we have those, then we can classify which is which among this Q hot and Q cold. You follow my logic here? Okay, so let's attack what is going on between A and B, guys. It's a constant volume process. Go for it. Work done at 0. First law of thermodynamics, read delta U equal to Q. W is disappear already. And you guys remember U is 3/2 NR the T. So the delta U is going to be 3/2 NR delta T. So far so good. And you even remember, but okay, I recognize vaguely that if you are looking at a constant volume process, that is like NC sub V delta T, right? Remember, there is a relationship between this CV and this 3/2 R right there. Cool. All right. So this is a very good review of
Okay.
what we did before. So from here, you will be able to just keep going and then you just say, okay, it's going to be 3/2. N is given to be 2 moles. So that is your N right there. R, I'll just leave it as R. Now you're going from A to B. So what I want here is going to be T final minus T initial. Yes. And because they already said the temperature at the hot reservoir is 600 K, the only thing left for you is, can you figure out the temperature at A? Can you? All right, let me once again, at A is going to be on another isotherm somewhere like that. Well, Ajahn, that's not too bad. I should be able to do that because A and B will follow VA over TA equal to B over TB. Yeah.
Okay.
Okay. And they are at the same volume. So the volume disappear. So now you see that the pressure at B is 3 times the pressure at A. So the temperature at B is supposed to be 3 times the temperature at A as well. Of course, 200K down here. Nice. So now you know the lower lying isotherm is already at 200K. So you are done. Okay, 2 cancel with the 2 here. So it's 3R T final 600, T initial 200, and that gives you the 400 Kelvin difference. At the end, I'm going to get 1200 R. That is your work done.
Okay.
I'm sorry, that is your heat. And it's going to be the delta U along with it as well. Isn't that nice? See what's kind of things supposed to happen. All right. And then once you complete this problem, you should be able to do any cycle in the PV diagram, right? Very easily. Okay, guys, can we move on? Let's go from B to C, shall we? All right, B to C. What happens, guys? It's the isothermal process. Delta U is 0. First law of thermodynamics, read Q equal to W with me because delta U is gone. And we have already seen this. It's the integral of PdV. We have done this. And okay, let me write everything down here. P equal to nRT over V dV. And then you integrate 1 over V, you get log V, put the V final and V initial to be your limits of integration. What you get at the end is nRT log of V final, which is V at C over V initial is V at B. And you are almost done.
Okay.
Isn't that nice? Okay. Now, N is known, R is fine, temperature is 600. The only thing left for you to do is just the ratio between the volume at C and at B. But then it's the same thing one more time. It's PBVB over DB equal to B CVC over DC, correct? Yeah.
Okay.
All right, just make it like, sound boring because you probably have seen this like a million times. And because they are lying on the same temperature, the TB and TC cancel. Okay, so it's just a PV equal to constant as expected because they are lying on an isotherm. So as you can see, the pressure at C is 1/3 of the pressure at B, just like before. So the volume is supposed to go 3 times. So whatever the volume over here is, the volume at C is going to be 3 times that to compensate for the lower of the pressure. Yes. All right, so now we know the ratio between the volume at C and the volume at B is going to be number 3. Very nice. So this is good. This is equal to 3. And that's it, guys. So I can say the heat over here is going to be N R T is 600 and then log 3. So I can put the answer to be 1200 log 3R. You are done in this segment here. Very nice. Keep going. Keep going. All right. Now you can see the end game is coming.
Okay.
Let's go from C back to A. And everyone remember, this is the constant pressure process. This is a process that you have all three terms to be non-zero. Okay. However, because we sort of have seen this 2 or 3 times already in the past, the heat, because eventually we want the heat, you can jump right into the heat by using the 5/2 nR delta T. You guys still remember this? Yeah. All right. Or this might ring a bell here. Here we go. NC sub P delta T. Yeah. And we got this one from where? We got this from delta U plus W. And we got it from 3/2 nRT over here from the delta U. And the W give you P delta V, which you can turn it into another nR delta T. Hence the 5/2 factor. Okay. I hope this sort of remind you those time that we did this. Okay. So that's very nice. So with this, then you can jump right ahead into the final answer. 5/2 N is 2, R, just leave it as R. Delta T is going to be T final. You arrived back at A. That's your final location. And then you subtract T at C. With me? Okay. I think the drawing is lacking, right? It's lagging to you as well, I hope. I don't know. It's just slow on my screen over here. Okay. All right. And that's it. 2 cancel. T final, T initial will give you negative. See that? You're going from 600 down to 200K. So final minus initial will give you a negative 300K change. Don't forget the sign. So it's going to be 5R negative 300 Kelvin. So at the end, you get negative 1500 R to be the heat during C back to A. Done.
Okay.
So I hope by showing you this part A of the problem here, this is what you need to consider. You have to figure out the heat by yourself based on the PV diagram that you have. All right. Now let me conclude what you're getting. You look at part A to B, guys. The end result that you have over here is this number right here, 1200 R. And as you notice, the sign automatically been taken care of as usual. It's a positive heat. So that means during A to B segment, heat flowing in. With me? Okay, so heat is flowing into the system. So when the heat is flowing in, I can draw an arrow and showing you that there is a heat flow into the system. And I can call this QAB just to signify it. This is the heat. It's crashes. Uh-oh. Oh, something is wrong right now. I don't know why. I will try to fix it. Maybe, I don't know, it's just because of the notebook or whatever. I don't know. But you guys still see this? Fine. It seems to be back right here. Okay, is it good? All right, okay. Yeah, it's good thing is they can reconnect and just put everything back. Okay, all right, guys, one more time. So over here, you can see that now segment A to B, you have a positive 1200 R, so that representing the heat QAB. I just put the subscript AB just to signify that this is during the AB process. That is a heat flow in to the system. Isn't that cool? Next, you see about Ajahn, here we go. I have 1200 log 3R is the heat during the BC process, and it's still positive. So that means during this BC segment, there is a heat flow in. So let me put another arrow right there. There is a, oh, it looks dirty here, but that's what it is. QBC is also in. All right, now let's move on to C to A. Now you start, you know, all right, I get it. Oh, whoa, whoa, whoa. I get it now. This is 1500 R, but you have a negative sign in the front. So now I hope you see the sort of the significance of keeping the order of the delta correct at all times, right? Because that gives you the sign of the heat flow. So over here, you have a negative heat. So this means heat is coming out. Let me put the arrow that's come out of it. So that's your QCA. And that is the heat that's flowing out right here. See? So that's complete the whole picture over here. That's, you know, all the heat flow during each segment. That's done for part A. So what happened to part B? How much work does this engine do each cycle and what is its efficiency? Can you do it now?
Okay.
I think you can. Yeah, because what you can see over here is now you know all about the heat. So, okay, come back here. Let me draw it nicely over here. You have, I just prepared this space just to clear the things out. I know it's gonna look very messy here. So I hope this helps. Here we go. So there's a heat flow in, 2 ins, and 1 out. Yeah. So what should be the work done, guys? Well done. By conservation of energy, it's going to be the QAC along with the QBC. Those are the two that comes in. And all you have to do is just subtract out the heat that is flowing out. QCA. And that will be your W. You guys with me now? Okay, let me compare this to the main diagram that we're going to have all the time. Heat Q hot, Q cold, and the work done. So the difference is just now, you have to know that at this point, the Q hot that we are talking about here is going to be the combination of the QAC and QBC now. So these two will contribute to the Q hot because these two are the heat that's flowing into the system. Okay.
Okay.
Yeah. And good thing is because you have only one segment that give you the Q that is transferring out. So that is still fine. The Q cold is still just the QCA right there. But with that, you should be able to guess right away about Ajahn. So what does it mean by you taking the difference between Q in and Q out? You're definitely going to get the W, but this W has to correspond to the definition of the W that we understood all along. It's just the area enclosed by this cycle. With me, guys? Perfect. And because this cycle run in the clockwise direction, so you're going to get everything as a positive number, we know, right? Because QAC is 1200 R. Okay. Here we go. I shouldn't write the positive side at this point. Okay, let me erase that one for now. Okay, so 1200 R plus QBC, that is just 1200 log 3R. And to subtract out the Q cold, 1500 R. And as you can see, if you work out this number, you're going to get a positive number right there. And as expected, because whatever the area that you get from here, the work done is going to be positive A because your cycle is clockwise. Okay, the area under the curve from B to C, and then you wipe out the area under the curve that's underneath right there. Remember that, yeah? You can go back and review that part. But at the end, what you are getting is going to be just the area that is enclosed by this cycle. And it's positive, so you get something out of this cycle. ทุกคน everyone okay? All right. And what is the efficiency of this cycle? But now it's easy. You have like flooded information. You can pick any numbers that you have already found, plug it into the definition. You can start even from the W over Q hot if you want. Okay, and don't forget the Q hot supposed to be 2, right? You're supposed to have these 2. That's your Q hot right there. Okay, all right. So that, I think that's the only part that, you know, many of you just is going to make mistakes, is just sort of assume that the Q hot coming from just only a single segment in the PV diagram. No, not necessary, right? It depends on the shape of the cycle that you are looking at on the PV diagram. And if you have more than segments that draw in the heat, you take those to be your Q hot, because that's the heat that is flowing into your system. Cool. All right. So that should be fine. And just one quick note, just make sure that at the end, you will have only just a pure number left as your efficiency, because efficiency cannot have any units. All right. And that's supposed to be. So, all right, you can do 1 minus Q cold over Q hot, whatever you like, up to you. Okay. So, all right. There you go. All right. Supposed to be pure number. And last one, okay, I can put this as a part B over here. And part C, compare this engine's efficiency with the maximum possible efficiency attainable with the hot and cold reservoir used by this cycle. So what this problem is saying is just like, hey, what if I were to use Kernel engine instead of this, you know, cycle over here? What efficiency will I get between these two reservoirs? And as you can see, the reservoir that you are running at is between 200K and 600K. So this make these parts very simple. The efficiency that we're talking about is going to be the Kernel efficiency, and it's going to be 1 minus T cold over T hot. And it's going to be 1 minus 200K over 600K. And that is going to be, what's that, 2/3? There you go. Something like that. All right. And as you can see, if you really just punch the calculator, or I mean, don't need to, but at least if you do the full calculation, this is going to be bigger. 2/3 is going to be the bigger than the efficiency that you calculated in part B, for sure, all the time.
Okay.
Is it fun? I know it's a lot, and I don't like it either, right? Just like I mentioned before, thermodynamics is the one that I at first hated so much because there's too many components, and it has the feeling just like biology that you have to memorize a lot. But it turns out once you dive into the detail of this one, actually it's just like other physics subjects as topics, that you have just only the, you know, just a few amounts of principle that you have to hang on to, and the rest you just apply those. But all right, I agree that for this particular thermodynamics topics, there's so many expressions that you have to memorize a little bit, sort of. Yeah. But I mean, in the end, it's, if you focus yourself within the first law of thermodynamics, it's the conservation of energy. Okay. And we are done.
Okay.
That's it, guys, for today. I think we have more than enough to move on. All right. And at the end, just try to answer your question. All right. And I hope this one actually cleared things up as well. So let me add an extra page here so it won't get matched with the other stuff here. So if your PV diagram showing the line that is straight line, a linear, yeah, like that. Okay, let me call this once again your A and B. Yeah. So this is your question, right? So you have just like a straight line linear process like this. What kind of thermodynamic process is this? It just have no specific name. That's it's fine. It's just a process. Okay. And to calculate heat and work, you follow the same logic here. Attack the easiest one first, which is W. Is the area under the curve. There's your W. With me? All right. So that's exactly what's supposed to be. It's an integral P dV. But even though this one, you don't need any integral because it's just going to be the trapezoid. So it's going to be the 1/2, the height, the sum of the two sides, S1, S2, or whatever your formula that you used to use. All right. Just find area under the curve. And if the process is going in this direction, so it means it's in direction that you are increasing the volume, it's guaranteed that whatever you get over here is going to be a positive number. Let's say, okay, once again, I'm just going to use this area to be A then, so it won't get, confused with the sign. All right, so the work done from A to B is going to be plus A. Second thing, attack the next easy one is the change in the internal energy. Once again, every point on the PV diagram must be lying on an isotherm. So I can imagine that point A and point B must be on some isotherm. So that means you must at least know what kind of temperature you're looking at. And this will give you a T hot and T cold. Cool. So once you know the temperature at point A and point B, then you can say it's always going to be 3/2 NR T final minus T initial. All right. And once again, sometimes you will be able to figure out this through PV equal to nRT. So it depends on the information in that problem. See? So as you can see, two steps, W and W does not change. It's just the shape of the curve just different, but the way that you calculate these two terms are exactly the same. And once you have that, the Q will follow, because from the first law of thermodynamics, delta U plus W will give you back the Q. But you already knew those two. All you have to do is just plug this thing in here, plug that thing in there. You will be able to calculate the W. And that will be your answer for 3 components in the first law of thermodynamics. Cool?
Okay.
All right, let's give it a shot. Go back to that problems one more time in the homework, and then sort of follow these steps and see if you can crack this one out. Yes, I will give you the answer keys soon. Don't want to give it too early because, well, all right, but I'll post the answer. Even though it's not a full solution, but at least you will have some reference for you to be able to, check your work. Okay, and if you still have questions, actually, I will be able to set up a Q&A before the exam. So once we decide when we're going to have the exam, before that exam date, usually I will have like Q&A session. So you can ask question, I can go through the homework together with you guys, whatever, just before the exam. All right, that will clear things up just before the exam. Cool. All right, guys. So if that is it, then I'll see you guys on Sunday morning. All right, and just be safe, and I'll see you soon. Bye-bye. Take care, guys.